Hi there, I am Martin McClure, and last year in Puerto Madryn I introduced the MIST project. I'm sure that some of you were there. I recognize some of you from that talk last year, but for those of you who are not, very quickly, the MIST project is an open source project to produce a variant of Smalltalk that's a little bit non-traditional in some of its aspects. I talked last year a lot about the implementation without a virtual machine. I'm not going to go over that again right now. We're going to talk about something different, but if you want to see that talk, you can always go to the FAST site, or that video is also at mistproject.org, which is where you go to find out information about the project in general. And you can find a pointer there to the code, which is on GitHub. And today we're going to be talking about some of the design features of MIST, the language features. We're particularly talking about reuse of functionality. Now, reuse in software is a huge topic, and we only have time for a tiny slice of it today. But in general, as Leandro was talking about earlier, software development is a process of decomposition followed by composition. You break your software down into pieces that are manageable. You break the problem domain down into pieces that are manageable. You make software components, you put them together to form your functioning system that meets your needs. Now, if you do this carefully and you do it right, then many of those components, those pieces that you put together, might be reusable for a different problem, and that's the core of software reuse. And so these components that you assemble together are what we're going to be talking about, and those components can be either very large or they can be very small, of all kinds of sizes. Like a large-scale component might be a package, say Seaside, which is actually many packages, but that would be a large-scale component. And a small-scale component would be something more along the lines of a class or a method. And today we're only going to be talking about the small-scale reuse, particularly the reuse of classes. So, one of the purposes of a class is to be a factory for objects. And so you want it to make all kinds of, many objects all having the same behavior. That's one of the functions of a class. And when you want to build this class that's going to be the factory for your objects, then you're going to possibly bring in other classes that other people have already written to use as components in some fashion. We're going to talk about some of the ways of doing that. But one of the things you're going to do is you're going to find that these other classes, they provide methods to you. And you might want to reuse a method. And so the methods that come to you in these other classes, there's basically one of four things that you can do with those methods. So you might want to expose that method. That is, you want your object to respond to that message, and you want it to respond in the same way as it did in the class that is your component that you're reusing. Or you might want it to respond to that message but actually do something at least a little bit different. So that's, you're changing the method in that sense. You might not want the method at all. I mean, you may get a class that gets a bunch of methods you want, but some of them you don't want. And those you want to omit, is the term I'm going to use. And some of them there's messages that the class that you're using as a component responds to these messages, but you don't want your objects to respond to that message, but you want to use that. So you want to use it internally to some of the functionality that you have. So I'm calling that using the method. So this is kind of abstract. So let's use a concrete example, a very simple one because we don't have much time. So we have a thing called temperature record. This is going to be used to record temperature readings over, say, a day. Every hour of the day you take a temperature reading and you put it in this object and it tells you a few things afterwards. So you've got these four messages that you can send to it. You can send it add with an integer to be the temperature reading, and you can ask it how many temperature readings you've done so far, and you can ask it for the average temperature throughout the day once you're done, and you can ask it what was the high temperature. And this is all it has to do. And there are going to be two components that we're going to look at that we might want to use for this. There's ordered collection, which, now this is a very simplified and slightly odd version of ordered collection for those of you who are very familiar with ordered collection as it exists in most Smalltalks. So it has two instance variables. It has size and then it has indexed instance variables to store its contents. And then it has these four messages. It has add, which adds to the end. remove, which takes the first matching one and removes it, and you can ask it for its size, which is how many things it contains, and you can iterate over the objects that are in it with do. So that sounds like a useful thing to have for this temperature record. And the other component that I'm going to say we have is we have a thing called an average keeper, and this thing has two instance variables, size and total. You can add an integer which adds to the total and increments the size. You can remove an integer which subtracts from the total and decrements the size. You can ask it for the average, which divides the total by the size, gives you the result. And then there's accessors for total and size. So these are the two components that we're going to use to build our temperature record. So let's look at what each of those methods we want to do with them. So size for ordered collection, that's how many readings we took. That one we can just expose because that actually gives us the answer we want in our temperature record. So we could just expose that. Add, however, we can't just add to the ordered collection. We also need to do an add to the average keeper as well. So we need to use that, but also change it because we want to respond to add. Remove is not in our specification, so we don't need it at all. And I'm going to say that we want to use do because we've made a design decision that there aren't that many hourly readings in a day, and we don't ask for the high temperature all that often. So instead of caching the high temperature, we're going to actually, every time somebody asks for the high temperature, we're going to iterate over all the readings we have and pick the highest one. And therefore, we're going to need the do method internally, but we don't want our temperature keeper, our temperature record to respond to the do message. So we want to just use that. And out of the average keeper, we want to expose the average because that's a message that we want to respond to, and we want it to give the average. We want to omit, remove, and total because we have no need for those. Once again, we want to change the add message because we've got two things to do with add now. And the size, this size also returns the correct thing, so we could just expose that. So let's take a look at how we might do this in Smalltalk 80. There's slight differences in some Smalltalks. For instance, modern Pharaoh has traits, and so there's different options there. But in Smalltalk 80, there's a couple of ways to do it. You can do object composition, which is where you build an object which has instance variables that hold your component objects, and you just send messages to them. And that looks something like this in Smalltalk. So we have our temperature record has instance variables called readings and average, and they hold. So we have a pointer to an ordered collection, we have a pointer to an average keeper in our temperature record, and our code looks like this. So add, we just send the add message on to both of our components, and that's the end of that job. And for size, we could forward this to either one because either component's size is going to give us the right answer. We just choose to do it to readings arbitrarily. Average, we must pass on to our average keeper. That's a funny looking method, but there you go. I probably could have named these things a little better, but hopefully you get the idea. And our high temp method, now neither of our components actually provides this, so we have to do it ourselves. So here we're doing it pretty simply. We just set something to minus 100, which we assume is colder than any temperature we're going to actually record. And then we iterate through our readings, and it picks the highest one by, at each iteration, seeing whether the one we've got is higher than our current highest. And then it returns that. And if you haven't taken any readings yet at all, it returns minus 100, which I am going to just by fiat assume is okay in this particular problem domain. So there we have our complete object. And one of the features of this is that when you use object composition, then you're just holding pointers to these objects and sending messages to them. This temperature record object has its methods have no way of accessing any of the internal state of these average keepers. So these instance variables here, these instance variables here, they're not accessible to the methods that are defined in the temperature record. And this is what's called black box reuse, because it's a black box. You can't see what's inside. You just send messages to it and interact with it that way. So there's another method, and one that's also very widely used in Smalltalk, class inheritance. So we can inherit from, we could say that one of those components was our superclass. And that's a common way of reuse in Smalltalk. But we can't in Smalltalk subclass from both of them at once, because it's single inheritance in Smalltalk. So we have to pick one or the other. So let's take a quick look at both. So here we've subclassed from ordered collection. And we still need the other components, so we're going to use object composition for that. So we still have an average instance variable and an average keeper instance hanging around. So what does that do to our code? Well, very little. We just do a supersend instead of a send to an instance variable for add. And we don't need a size method now because we've inherited it from ordered collection, and that actually gives us the right answer. We forward our average method just like we did before. And our high temp method looks very similar, just this self send instead of a send to a component. So that works reasonably well so far. But we have also inherited the remove method and the do method, and I've lost my colons on my graphics for some reason. But anyway, we have inherited these methods, and we don't want them. So, well, there is a way in Smalltalk to deal with that. We can say self should not implement for remove. And we also don't want the do, so we can do self should not implement do. All right, now who sees the problem with this? Okay, right. Here, we do a self-send of do, because we want to use that. And now that we've done this, that is going to break. So there is a way to do that, and that is to change it to super. This is generally considered to be a very bad idea. Very fragile code, very bad form, basically. It will work. But that forces the superclass method to be invoked, but because we're sending super do and we're in a method called high temp, the good form is supposed to be use that only within the method of the same selector as what you're sending the super send to, like we did with the add. But we can do it, and that does work. So that's how inheriting from ordered collection would work. Let's take a look at inheriting from average keeper. So once again, we have to do the other thing as a component. So we have a readings instance variable again. And let's look at our code. So once again, we send to a component, we send to super. And once again, we inherit a size method, this time from average keeper, but it does the same thing, gives the same answer. So we're happy with that. And we also don't need an average method because we've now inherited that. So this is looking better already a little bit. And our highest, we just send it off to readings, and we don't have to do the ugly super trick. We do still have to add a couple of should not implements for, in this case, for remove and for total for the messages we don't want. And should not implement is just a little bit ugly because, like if you ask this temperature record object now, do you implement the total method? Do you respond to total? And it will say yes. But if you try to send it, it will say, error, sorry, fooled you. So it's just a wee bit ugly. I don't like that. But this does work, and it's a little better than subclassing from ordered collection. And I want to take a moment and talk about super, because super is a very odd thing. Every time you send a message in Smalltalk, you are sending a message with some selector to some object, and the receiver of that message decides what method that means to execute based on its class and its superclasses and that sort of thing. And supersends don't work that way. Supersends are only determined by the position in the code that you actually write the supersend. It's always in the superclass or somewhere up the superclass chain of the class in which the method is defined. It has nothing to do with what the class of the receiver is. It's all about where the method is, where the send happens. So it's all about code position instead of the object. So it's a very strange thing. I'll get back to that a little later. So because in this case the instance variables are all visible to the subclass, and the methods can be completely overridden, then class inheritance is usually referred to as white box reuse, because you can see what's inside the box. So that's small talk. Let's see what things are the same and what things are different in MIST. Well, first of all, there's object composition. Now, object composition in MIST works exactly the same way as it does in Smalltalk. So I won't talk any more about that. But MIST no longer has inheritance at all. So last year I showed this slide, the traits, the cover of the traits paper, Nathaniel's thesis, which I highly recommend to anybody who finds this talk interesting. And I said that I wanted to have traits. Traits are basically groups of methods that you can compose together in combinations without ordering to add functionality to classes. And traits are a way of extending inheritance to give more functionality. But I said I wanted to add instance variables to traits. And after the conference, I was walking in a park with Andres and in Buenos Aires right after the conference, and he said, well, once you add instance variables to traits, they start looking a lot like classes. Do you really need both concepts? So on the very long flight home, I started thinking about this, and it took a while to get comfortable with the idea. But yes, you do only really need one concept, and we need more practice with what I've come up with to see whether it really works in actual development of large software systems. But I'm pretty happy with it so far. And so what I did was I came up with classes that compose but do not inherit. They compose like traits. So let's get some of the terminology out of the way. So you compose a composite class from component classes. Now how does that look at our little temperature record example? So in this case now we have a temperature record class, and it is being composed from the two classes, average keeper and ordered collection. Now what happens, and we specify that with something that looks like, I've sort of made this up. It's partly based on the traits composition stuff, and it's partly I just made it up, and it may change before the final stuff happens because none of this has been implemented yet. It's just design at this point. And I'm telling you about it once again because I want feedback on the design. Why implement something until people have had a chance to comment on it? So one thing I want to point out is that it doesn't matter what order you say it's composed of. It's completely order independent, just like traits. And by default, what you get when you compose classes is you get the complete union of all of the instance variables, and you get the complete union of all of the methods. So we should get all of these methods by default and all of these methods, and as you see here, we actually have all of the instance variables, including two that are named size. We will talk about the instance variables later. Let's deal with the methods first, because we know we have some methods in here that we don't want. We've got these removes that we don't want, and we've got a total that we don't want, and that sort of thing. So as in traits, you can omit those explicitly just by saying, well, for ordered collection, I don't want remove, and for average keeper, I don't want remove total or size. And we say that because we don't need the two size methods. They return the same thing. So the size here is not going to be, it's going to be this one that came from ordered collection. It's not going to be the one from average keeper because we've omitted it. But we still have the problem of what to do about add. We have an add method here, and we have an add method here, and we have an add method here that needs to do something different than either one of those, and all three names conflict with each other at this point. And as in traits, conflicts must be explicitly resolved. You have to say what you want to do about any time there's a name conflict. So since we want to actually change the behavior of these, because we want this add method to invoke both of these add methods, one after the other, although we don't care about the order, what we will do is we will alias, as in traits, to the names of those methods that we got. So we've added now these alias add to OC add for the ordered one that came from ordered collection, and these names are totally arbitrary. And we alias add to AV add for the one that comes from average keeper. So that kind of takes care of our methods. We now have no conflicts. We have a legitimate object that actually has, that's inheriting the methods we want to, well, not inherit. It actually has the methods composed that we wanted to have composed. And our code looks like this. So for add, we say self OC add and self AV add, because we've aliased those. So that invokes those two methods that we've got by composition. Size and average, this size method has been composed in, so is this size method. This average method has been composed in, so we get that. And once again, we have a high temp, and here we're just saying self do, and it does its thing like it always has. Now we still have the problem that do is something that we don't want our object to respond to. We also have introduced an OC add and an AV add, and we don't really want it to respond to those messages either. So in MIST, I've added one more concept which goes beyond what traits do, which is that you can make things private. So we make do private, and we do an alias to private name, an alias to private name for OC add and AV add. And now what being private means is this method is only available to self-sends. So a self-send with any of the methods that are within temperature record, like the add method or the high temp method, which are the two that are defined in temperature record, as opposed to these two methods, which are defined one here and one here. These methods that are defined in temperature record, any self-sends they do of these OC add, AV add, or do are going to work. But anybody sending a message to an instance of temperature record that sends that message to that instance is going to get a does not understand. Yes?
What about self yourself do?
Very good. Self yourself do is not the same. This is a syntactic thing. So yes, it's not just you happen to get a reference to yourself, but the syntactic form of self sends. So yes, if you wanted to see what an outside entity sending a message to that, then self yourself would, and for anybody who hasn't been introduced to that concept, yourself is a message that always returns the receiver, which sounds completely useless, but in fact is useful in some cases. And one of the other things about this, when I started mushing the concepts of class and trait together, I had a big choice to make between white box reuse and black box reuse. And I chose black box reuse partly because it was less familiar and partly because it seemed easier for this particular problem. One of the values of MIST is to try the unconventional thing first because you already know how the conventional thing is going to turn out. If the unconventional thing doesn't work, you can always go back and do the conventional thing because the MIST system is as simple as it can possibly be. So the cost of actually being wrong about something is lower because rewriting a large portion of the system is actually not that expensive. That's the idea anyway. So we chose black box reuse. And so therefore, that brings us to what we can do about the instance variables. So these instance variables are all private to the class they were defined in. So this size in total, which happens to be this size in total, they're private to these methods. And these methods can access those instance variables. And our newly defined add and high temp methods cannot. And this size and these index instance variables are accessible to these methods. But once again, our newly added add and high temp methods, those cannot access these instance variables. One of the advantages of doing this, besides just isolating things and making them a little cleaner, hopefully, is that you don't have to worry about the fact that there are two instance variables named size because the methods that can access them come from different worlds, so there's never any ambiguity about which one you're talking about. It does make some things, it is going to make developing large software systems a bit different. And I have some speculations that I don't really have time to go into about how that's going to work. I think it's going to work pretty well, but it's definitely going to be different. And then there's those self-send rule, and I would like to point out that self is weird. So, because there are no subclasses and no superclasses, there is no super keyword in MIST. I had to actually redo the logo because it had a super keyword in it last year when I showed it to you. And there isn't that anymore. So I've eliminated one weird rule, but I had to replace it with an almost identical weird rule, or at least similar in spirit, in that, once again, self, syntactically, in the code, means that send, what it's going to do, depends on its position in the code, not on the class of the receiver. That's only true if the selector that it's sending is defined in that class. If so, it will always find that method. If not, it will be a normal self-send as we're used to in Smalltalk. So that is pretty much it. So to recap, we've got object composition, which actually I think is in either MIST or Smalltalk. I think this particular example of temperature record, object composition is a really great way to go. In Smalltalk, it's clearly superior to class inheritance as far as the cleanliness of the code. And it's kind of a tie with class composition for this tiny example. But the big differences are that, in object composition, what happens by default with all those methods is if you don't do anything, they're not there. Right? If you want to pass those messages through that your components accept, then you're going to have to write a forwarding method. So there's a little bit of work there. But it's really easy to use the things within object composition as well. So in object composition, if you don't want to expose much, and you do want to use a bunch, then that's a really good way to go. Whereas with class inheritance and class composition, then exposing it is the default. So if you want to expose a lot of methods, then that would be a good choice to either subclass from your component that you want to reuse, that you want to expose a lot of messages from, or in MIST you can actually expose a bunch from multiple components, or in say Pharo where they have traits, you can also do that. And yeah, the rest of that chart is kind of hopefully self-explanatory. This is that supersend with the should not implement, that ugly thing. And if you're not willing to do the ugly thing, then you actually can't do this pattern with class inheritance. I think the biggest difference between class inheritance, possibly with traits, and class composition is class composition has a little bit fewer concepts involved in it, so I like it better from that perspective. But the biggest difference is the black box versus white box. And I think that's going to be what makes the biggest difference in actually using this scheme to develop software. And I'm really interested in seeing how that turns out, because I really don't know how it's going to turn out. So that is it. Remember, once again, go to mistproject.org to see previous videos or this video once it's up, and participate. Join the mailing list, which is very low traffic, but every once in a while there's a little burst of people talking about something or other. And thank you very much. Any questions? Richie.
Yeah, I'm running ahead because I heard this like 10 minutes ago, so I've been thinking about it. But with this, you lose the chance to build, I don't know how it's called, but something like a framework in a class where you prepare a class to have subclasses that implement a little bit of differences, like little behaviors, like. So the superclasses has everything, so you can collect something, and the behavior for each subclass is different. It's a bit different.
Mm-hmm.
So I was just discussing with him that he could have something. You understand the problem, right? It's like, I don't know how it's called, but
yeah, we should talk about the specifics of what you're talking about. I'm not quite sure I get it. I think you can.
When you have a class, and each subclass implements one method, a bit different.
Yes.
So if you parameterize this, right. So parameterize is an algorithm, for example.
Oh, right. Yes.
Something
Yes.
like that.
Okay.
So you couldn't implement that here unless you have something that's the opposite of super, that would force the superclass to use the self as we know it today.
Right. Yes. Well, the component class, which would be the superclass in inheritance, right? It can do a self-send of a method that it does not implement. and then it would expect that to be implemented by anyone who, and that would be an abstract class because it is not complete. And then when you incorporate it in, it does the self-send, and that is locally resolved to where it's been composed into.
So if it's not implemented?
Yeah, if it's not implemented, it's a normal self-send, yeah.
So you won't be able to subclass.
Right. Otherwise.
So how different would that be? You tell from, or how would that differ from the case where you compose from one class?
Well, I think it would be very similar. If you compose from one class, it is very similar to single inheritance. The biggest difference is, again, the white box versus black box. You don't have access to the instance variables. You really don't have as much control over that, which means you can't. I know that a lot of people, they take someone else's code, they subclass from something, and it wasn't made with their situation in mind, so they have to do a bunch of weird stuff to fix it, and they kind of grope around in the internals to do that, and you can't do that with black box. So that's a limitation. On the other hand, once people have done that, it becomes very fragile code, and the person who implements that superclass, if they make any little change to their internals, they probably break this subclass that someone else wrote, and that won't happen as much, I think, in a black box world. So there's some trade-offs here. I'll be interested to see how it happens.
Yeah, I think the big question here is class composition better than object composition? Because
right.
The inheritance, class inheritance, at least for this example, is not the right thing to do. You can do it, but definitely it's not the way.
Right.
And looking at the code, it looks like class composition. You have to take care of more stuff than the object composition, because the object composition you only have to forward some messages and implement only what you need. What is the other? You have to remove, make private, those kinds of things, and at the same time, from the evolution point of view, as you put there, it evolves better the object composition idea than the class composition.
Okay, I really think that object composition is still a very good way to do things. And I think the case where you want to use class composition is now if you look at the traits, examples of refactoring the collections hierarchy and things like that, where there's a little collection of methods and you really want those, and there might be instance variables now, and you want to expose almost all of them. This saves you writing all those forwarding methods, and then you don't have to do all of this other stuff. So I think there are some cases where class composition is the natural way to do it, and some where object composition is definitely better. I don't think that object composition is going to go away or should go away. This does not replace object composition at all. It does replace inheritance, but object composition is still a fine way to do things.
Still have time if there are more questions.
Yes.
I have one question. One of the consequences of using traits for solving problems that are similar to the one you solved is that you generate an amount of code that can be used to, for example, mix the behavior between two classes or to choose, actually, not to choose one, you don't need to go for that. Just compose me. My question is, you still have these problems when you compose classes, right? You need to write new code. For example, if you want to use the size from both classes.
Like with the add in my example where you had to send both messages. Yes, you do have to write some glue code. I think one of the advantages over traits is that in traits you needed glue code to access all instance variables, and here instance variables come along for the ride and the methods can actually access those. So I think it's probably, once again, no actual experience using this, and and I think that's what's going to really tell. But I think it's going to be a little easier to use than traits just for that.
One more question. Have you made an implementation? These are basic one. Does Latin
It's the implementation of MIST is not that far yet, but I do have a design for how to do it. Yeah, the simplest design is to pretty much flatten. There are cases in which the methods can be shared between. Excuse me. The methods can be shared and don't have to be recompiled for the composed use. Especially if they don't access any instance variables, or the instance variables they access end up at the same offset within the object. If you are working with a technology where the compiled methods do refer to instance variables not by some indirect means, but by physical offset within the memory of the object, which the current plan for MIST is to do it that way. So yeah, there's some cases where you can do that. I mean, there's design trade-offs. There's a number of possible ways to do it. Todor.
Yeah, you implicitly include of the method of the class to compose, and you explicitly reject some of them, like the photo methods, etc. Why not the other way around? Why not explicitly making everything private and only explicitly publishing some of them?
That's an interesting question. I mostly am following the example of traits, and I think that because it's like this is the default. But there is, if we see very many cases where you want to do the other thing around, and I think that if it's the other way around, I think object composition works fine. You don't need anything else. But if we did, we could add a simple thing that says, compose omitting, that would basically reverse the default for that composition, and then you could. That particular class would be composed using the other rule, or that one class would be composed in using the other rule. I mean, that's certainly possible to do, but, right now I'm thinking object composition is the way to go for those cases. All right. Thank you very much.